I am Anna Sahib Gorane from Rayat Shikshan Sanstha's RBNB College Srirampur. In last lectures, we have studied about the optics, different phenomenon related with light. We also know the distance of distinct vision. The minimum distance of an object from unaided eye at which object can be seen clearly without causing strain to eye is distance of distinct vision. For normal human eye, this distance is about 25 centimeter. Now we know some optical instruments such as microscope, telescope. They are used to increase the visual angle of the object. The lens makers use convex lens, or watch repairers use convex lens to see small parts of watch while repairing, or to read small letters we use a convex lens. The convex lens used in this way is nothing but simple microscope, or it is a reading lens. So what is simple microscope? It is a convex lens of small size and small focal length. If object is placed within its focal length, its virtual, erect and magnified image is formed on the same side of object. What is the main thing? Object within focal length. Within focal length of the convex lens having small size and small focal length, image formed is virtual, that is, it is not real, erect and magnified, and it is on the same side of the object. The convex lens used in this way is called as simple microscope. Convex lens used in this way is a simple microscope. Now we see the expression for magnifying power of simple microscope. Magnifying power of simple microscope. Magnifying power of the simple microscope. Firstly, we draw the ray diagram of simple microscope, and then we see its magnifying power. How to find the magnifying power of the simple microscope? Convex lens, this is the pole. Object is placed within its focal length. This is the object AB. It is placed within the focal length. This is the pole of the lens. These are the incident rays. If these rays are produced, they meet each other at single point, and at that point we get the image. This AB is an object. We get image at A dash B dash. At this point we get the image. Here this angle is a beta. Distance of the object from the pole is object distance, it is u, and distance of the image from the pole is v. So this is the ray diagram for image formed by a simple microscope. Here visual angle is beta. This is image formed by simple microscope. Visual angle is beta. If the same object we can see directly without using the lens, its observed size is maximum at ddv. See second figure. If the same object AB we can see it directly without using the lens, its observed size is maximum at ddv. If we see this object directly, this is I, this angle is alpha, and suppose this distance is d, that is the distance of distinct vision. This is the second figure. Here visual angle is alpha at I. Visual angle alpha, visual angle made by the object alpha at I by object at ddv. See these two figures. First figure is image formed by the simple microscope. Here this object AB is placed within the focal length of the convex lens. Its image is A dash B dash. Image is virtual, it is erect, same as the object, but it is magnified. Image is virtual, erect and magnified, and it is on the same side of object. The convex lens used in this way is a simple microscope. Beta is the visual angle of the image at the eye. It is also a visual angle of the object at the eye. P is the pole of the lens, u is object distance, v is image distance. Here object distance is u, image distance is v. If the same object, if we see directly without using the lens, its observed size is maximum when it is placed at distance of distinct vision, that is d. If it is placed at d, and that is the visual angle alpha at I if object is directly seen without using the lens. Now we have to find the magnifying power of the simple microscope, or we have to find the angular magnification. So magnifying power or angular magnification of the simple microscope. Angular magnification. Now we know the definition of this magnifying power. It is the ratio of visual angle of image to the visual angle of object if object is at DDV. So it is magnifying power is visual angle of image, ratio of these two quantities, visual angle of image at I to the visual angle of object at I if object is at DDV. It means this MP is visual angle of image is beta, visual angle of object if it is at DDV it is alpha. So this magnifying power of the simple microscope or angular magnification is beta upon alpha. For the small angles, tan beta is nearly equal to beta and it is AB upon U. Tan beta is nearly equal to beta and it is AB upon U, that is the object distance. Similarly, tan alpha is nearly equal to alpha and it is AB upon D. AB upon D. Suppose this is equation 3. From equation 2 and 3, that equation 1 becomes magnifying power is equal to beta, that is AB upon U, alpha, that is AB upon D. So this magnifying power of the simple microscope is AB get cancelled and it is D upon U. Suppose this is equation number 4. Magnifying power is equal to D upon U. Now here we know the lens formula. By lens formula we know 1 upon V minus 1 upon U is equal to 1 upon F. 1 upon V minus 1 upon U is equal to 1 upon F. Suppose this is equation, next equation 4. Here U and V are negative by the sign convention, but F is positive as it is a convex lens. Hence we write U and V are negative. As this is negative, minus 1 upon V. Again this is negative, U is negative, minus minus plus 1 upon U is equal to 1 upon F. Therefore this 1 upon U is 1 upon V, that becomes plus 1 upon F. Multiplying both sides of this equation by capital D, we get D upon U is equal to D upon V plus D upon F. But from equation 4, magnifying power is D upon U. Magnifying power is D upon U. So magnifying power of simple microscope is equal to D upon U, but this D upon U is D upon V plus D upon F. Equation 4, suppose this is equation 5 and suppose this is equation 6. We get the expression for the magnifying power of simple microscope as d upon v plus d upon f. Now we consider some limiting cases here. When the magnifying power is maximum, when it is minimum, we see some cases. These cases are also important. Case first. This is the expression for the magnifying power. If image is at distance of distinct vision, if image formed is at distance of distinct vision, it means image distance is d, v is equal to d. Then this equation 6 becomes magnifying power is equal to, substitute here v as d upon d plus d upon f. So magnifying power is 1 plus d upon f. Equation 7. And this is magnifying power when image at ddv, that is the distance of distinct vision. Now case second, if image is at infinity, if image formed is at infinity, we write image distance v is equal to infinity, and if we substitute that value in equation 6, we get value of v as infinity. So magnifying power is equal to d upon infinity plus d upon f. But 1 upon infinity we know it is 0. So this part will be 0 and we get magnifying power as d upon f. This is suppose equation 8. And this is the magnifying power if image is at infinity. Image at infinity. See the equation 7 and 8. From this equation 7 and 8, it is clear that the magnifying power of the simple microscope is minimum for the image at infinity. It is minimum, MP is minimum for image at infinity, and that is d upon f. At infinity, image at infinity, and it is maximum for the image at ddv. Magnifying power is maximum, and that maximum value is 1 plus d upon f if image is at ddv. And from this expression it is also clear that this magnifying power is inversely proportional to focal length. If focal length is small, magnifying power will be large. So this is about the magnifying power of the simple microscope, or it is the angular magnification of the simple microscope. Now we see one numerical based on this concept, that is the magnifying power of the microscope from our textbook. Numerical is also simple. See the numerical based on this. A person uses spectacles of number 2. .00, that is 2. There is a power in diopter for reading. Full stop. Determine the range of magnifying power. The range of magnifying power, we call it as angular magnification. Possible range of magnifying power possible. That is the possible range, maximum and minimum values of the magnifying power we have to find. It is a concave convex lens. It is a concave convex lens. N 1.5, refractive index of that lens is 1.5. Of one of its surfaces to be one of its surfaces to be 10 centimeter. Concave convex lens, if one of its surfaces to be 10 centimeter, that is the radius of one surface is 10 centimeter, radius of curvature of the one surface, estimate that of other. One of its surfaces means here radius of that one of the surface is 10 centimeter. We have to find the radius of curvature of the other. Now here the number of the spectacle is 2, it means it is the power. So given is power is equal to 2 diopter, and as we know P is equal to 1 upon F. Therefore F is 1 upon P, that is 1 upon 2. F is 0.5 meter. And we also know the distance of distinct vision for normal human eye is 25 centimeter, that is 0.25 meter. We know this value for the normal human eye. The range of magnification or magnifying power, we know magnifying power is minimum for image at infinity, and its value is D upon F. Minimum magnifying power is D upon F, that is 0.25 upon 0.5, and that is 0.5. Minimum value of magnifying power is 0.5. Magnifying power maximum, we know it is at DDV, and it is 1 plus D upon F. That is 1 plus this D upon F, we already know it is 0.5, so that is 1.5. So maximum and minimum values or the range of magnifying power is, minimum value is 0.5 and its maximum value is 1.5. Now see next part. In next part it is given that the refractive index is 1.5. One of the radius is 10 centimeter. Suppose that radius is R1 and as we know focal length we already find, that is 0.5 meter or it is 50 centimeter. As this radius is centimeter, we convert that focal length in centimeter. By the lens maker's equation, we know 1 upon f is equal to n minus 1 upon r1 minus 1 upon r2. 1 upon 50, f is 50. 1.5 minus 1, 1 upon 10 minus 1 upon R2. 1 upon 10 minus 1 upon R2. This subtraction is 0.5. And so next step will be 1 upon 50 into this 0.5 here. That is equal to 1 upon 10 minus 1 upon R2. This subtraction is 0.5. 50 into 0.5 is 25. So next step is 1 upon 25 is equal to 1 upon 10 minus 1 upon R2. 1 upon 25 is equal to 1 upon 10 minus 1 upon R2. But 1 upon 25 is 0.04. Very simple part. 1 upon 10 minus 1 upon R2, and therefore 1 upon R2 is 1 upon 10 minus 0.04. 1 upon R2 is 1 upon 10 minus 0.04. Next step, 1 upon R2 is equal to 1 minus that 0.04 into this 10, that will be 0.4 upon 10, that is 0.6 upon 10. 1 upon R2 is 0.6 upon 10, so R2 is 10 upon 0.6. Take the reciprocal, R2 upon 1, 10 upon 0.6, or we write it as 100 upon 6, or that is 50 upon 3. So next radius of curvature is 50 upon 3 centimeter. This is our second answer. So this is about the simple microscope. Today we stop here. Thank you.